A very warm welcome this afternoon to our session on dect, the thing that most of us use and sometimes misuse or even abuse. Before the stage is open for our speakers, the usual thing on not blocking the doors. Right now we seem not to have any problems. Anyway, the third team asked me to ask you not to block any doors. Okay, have much fun with these nice guys and dect. Thank you.
Okay, so we're a bunch of researchers who've been looking.
Microphone.
Okay.
Mic.
We're a bunch of researchers who've been looking into dect and especially the security of dect networks in, well, I think the last couple of years. So I only started a year ago, but we have people who've been at it for longer than that. So let's start by introducing who's on the stage, and then we'll tell you who the rest of the project is, because it's kind of large. So.
Yeah, my name is Erik Teves. I'm a researcher at TU Darmstadt at the cryptography research group of Professor Johannes Buchmann, and I studied computer science for years in Darmstadt, and I'm now a PhD student since a year in Darmstadt. And I'm also a member of the Chaos Computer Club, and I think I'm here since 10 years or so. So I was at the Congress every year since 10 years or so.
Okay, my name's Ralph Wyman. I'm currently at the University of Luxembourg in the LAX lab of Alex Buyukov. And yeah, I've been in Darmstadt before, and that's how Eric and I know each other. And this is
Andreas Schuler. I'm member of CCC Trier. I'm working on reverse. Yes, this is Masu.
Yeah, my name is Matthias Wenzel. I come from near Munich, and I was in the project. I was involved mainly in writing the Linux driver for the PCMCA cards. Yeah, and some reverse engineering of the chip layout, the cipher, and yeah, things here and there.
Okay, so besides that, we had people from Weimar involved in the cryptanalysis, which was Stefan Lux. Then we had people here in Berlin, among others, Starbuck and Carsten Knoll, and people in Wiesbaden who worked on the Kismet integration. That was Christian Frommer. So, one little thing. Part of this talk will be held in German. I know this might annoy some people, but it's better so the technical details can be understood by those who speak German. We will switch over to English later again. The slides, however, are all in English. And if you have any questions, feel free to ask.
So, also ich werde jetzt etwas über Ich werde jetzt eine Einführung in dect machen. Also fangen wir erstmal an, was war vor dect? Da gab es CT1 und CT1 Plus. Das war alles komplett analoge Kommunikation, war nicht sehr gesichert. Der Upstream lief auf einer anderen Frequenz wie der Downstream. CT1 ist inzwischen nicht mehr verfügbar, also die Frequenzen sind belegt von GSM. CT1 Plus, mit dem passiert das Gleiche am 01.01.09. Dann gab es CT2, das hatte schon ein Time Multiplexing. Also es wurde eine Frequenz für Upstream und Downstream benutzt. Das Ganze war nicht verschlüsselt, es gab keine Authentifizierung und eigentlich hätte jemand etwas gebastelt, hätte man auch auf die Nachbarn telefonieren können. Wo wird dect überall benutzt? Klar, in Schnurlustelefonen, in Wireless ISDN-Geräten, also zum Beispiel Internet auf einem, also es gibt FreePads, kleine tragbare Computer mit ISDN-Netzwerk. Dann in Babyphones wird es benutzt. Es gibt auch so Emergency Call Geräte. Das heißt, da hat man einen Knopf und dann wird automatisch der Notruf gewählt, wenn die Oma umkippt oder was weiß ich. Es gibt Türöffnungssysteme, also dass die Sprechanlage von der Tür direkt über das Decktelefon gesteuert wird. Klingelt jemand, hebt man ab, hat die Sprechanlage, kann mit dem Kerl vor der Tür reden. Man drückt dann einen Knopf am Decktelefon und die Tür geht auf. Auch sehr nett. Dann gibt es EC-Geräte, also EC-Kartengeräte, schnurlose. Habe ich vor kurzem noch damit bezahlt, jetzt eher nicht mehr. Und dann seit neuestem soll irgendwie Verkehrsregelungen, da gibt es ein Projekt über oder mit dect, Ampeln etc. gesteuert werden.
Das gibt es schon seit längerer Zeit. Siemens verkauft solche Lösungen, die angeblich auch, also die in England im Einsatz sind.
Mehr als nur Ampeln, Verkehrsleitsysteme.
Also die Situation in Deutschland, die Verbreitung ist sehr groß. Also ich habe mich selbst gewundert, selbst meine Oma hat so ein Ding. Wir sind dann mal durch ein Dorf gefahren und haben mit den Einwohnern hochgerechnet, wie viele Stationen wir gefunden haben. Und da waren wir bei 30 Millionen, hochgerechnet auf Deutschland. Ein paar Abkürzungen, die öfters fallen werden. Alles klar? Ja. Ein paar Abkürzungen, die öfters fallen werden, ist zum einen mal FP oder Fixed Part, das ist die Basisstation. Dann gibt es Portable Part, PP, das ist das Telefon oder was auch immer, das Gerät, was halt tragbar ist. Die RFPI, die kann man in etwa vergleichen mit der SSID bei WLAN, also nicht ganz, es sind noch ein paar Bits zu Zugriffsrechten und so. Das kann man ganz schön erkennen. Also wenn eine RFPI vorne mit 1.0 beginnt, weiß man, das ist eine größere Anlage. Wenn sie mit 0.0 beginnt, das ist dann irgendwie ein Konsumergerät oder sowas. Das ist auch genauer definiert, aber ja. Dann gibt es noch die IPUI. Damit wird, wenn ein Gerät angemeldet ist, ein PP, dieses im Netzwerk angesprochen. Dann gibt es noch DSC, den Dect Standard Cipher. Das ist einer der zwei Algorithmen, die geheim sind, die man nur gegen Geld und Unterschreiben vom dicken Vertrag und Verpfänden von Haus und Hof bekommt. Genauso der DSAA, das ist der zweite Dect Standard Authentication Algorithm. Und den UAK, das ist der Key, der mit dem DSAA ausgetauscht wird und den PP und FP zusammen benutzen zum Authentisieren und zum Verschlüsseln auch?
Nee. Zur Generierung des Verschlüsselungsschlüssels. Entschuldigung, Jan. Zur Generierung des Verschlüsselungsschlüssels, also zur Generierung des DSC Cipher Keys.
dect ist, also kommen wir überhaupt mal zu dect. Dect ist spezifiziert von der ETSI im EN 300-175. Die Kommunikation funktioniert komplett digital, also nichts mehr analog. Es ist GFSK-Modulation, das kann man sich ähnlich vorstellen wie ein digitales FM. Meistens, also bei den meisten Geräten mit 2 Zuständen, aber es gibt auch, also spezifiziert ist, glaube ich, bis zu 16 Zustände pro einem Takt, die möglich sind. In der EU gibt es 10 Carrier mit maximal 250 Milliwatt Sendeleistung zwischen 1880 und 1900 Megahertz. In den USA gibt es nicht ganz so viel, sind es nur 5 Carrier bei 1290 bis 1920 bis 1930 Megahertz mit 100 Milliwatt. Das nennt sich dann dect 6.0. Es gibt noch weitere Bänder, wo es spezifiziert ist, aber da haben wir bis jetzt keine Geräte selber benutzen können. Channel Spacing zwischen den einzelnen Carriern ist 1,728 Kilohertz und diese Kanäle sind aufgeteilt in 24 Timeslots. Das sieht dann so aus, also da haben wir einmal die 10 Carrier. Jeder dieser Carrier ist aufgeteilt in 24 Timeslots. Die ersten 12 sind Upstream, das heißt Station sendet, Gerät hört zu. Die nächsten 12 sind Downstream, Gerät sendet, Station hört zu. Und zwar, wenn die Station in Slot 0 sendet, dann antwortet das Gerät in Slot 12, also immer 12 verschoben, die sind einander zugeordnet. Ja, so ein Paket ist aufgeteilt erstmal in S-Feld, also Präambel und eine Paketkennung. Dann kommt das A-Feld, da läuft das Signaling drin. Dann das B-Feld, da laufen die Daten drüber. B-Feld gibt es nicht immer, halt nur, wenn man wirklich eine offene Kommunikation hat. X gehört eigentlich noch zum B-Feld, also das X-Feld, das ist die Checksumme vom B-Feld. Habe ich jetzt aber deswegen extra hier, weil das Z-Feld ist die Kopie vom X-Feld und wird dazu benutzt, falls mal eine zweite Station da ist und das Paket in diese reinrutscht. Also wenn die Z-Bits beschädigt sind, sollte man den Slot oder gleich den Kanal wechseln, weil man sonst gleich kaputte Pakete hat. Dann gibt es noch einen kleinen Space, dass man keine Überschneidungen hat beim Senden vom nächsten Slot. Ja, weiter. Dann gibt es Scrambling. Also Scrambling wird verwendet, um ein DC-Offset auf dem Signal zu verhindern. Also zu viele Nuller oder zu viele Einser machen Probleme beim Senden und Empfangen. Aber nur das B-Feld wird gescrambled mit dem LFSR, das hier dargestellt ist. Dieses wird initialisiert durch eine Zahl, durch die Frame Number, diese wird gebroadcastet von der Station. Ja, das LFSR ist spezifiziert in dect und ist frei zugänglich. Also ist kein Sicherheitsmerkmal oder sowas, sondern reine Hilfe beim Senden, Empfangen. Dann gibt es noch Verschlüsselung. Falls diese aktiviert ist, werden manche Pakete beim A-Feld verschlüsselt, die zum Aufbauen von einem Kanal, also von einem Anruf, wo auch die Pakete drüber gehen, was gewählt wird, also welche Nummern gewählt werden. Und das B-Feld wird komplett verschlüsselt. Wie verhalten sich die Geräte? Also die Basisstation, die broadcastet normalerweise ihre RFPI, ihre Kennung also. Die broadcasten noch ein paar andere Informationen, wie die Frame Number, die Multiframe Number und sowas. Und sie scannt auf allen ihr zugänglichen Slots, ob sich hier ein PP-Gerät meldet. Und zwar bei jedem Frame wechselt sie den Kanal. Also ein Frame sind 24 Slots. 24 Slots. Wechselt sie den Kanal auf den nächsten Kanal und scannt dort weiter. Moment. Das Telefon, das hat schon etwas mehr zu tun. Normalerweise in Idle Mode sendet dieses gar nicht. Ist also komplett still. Kann man auch nicht irgendwie detektieren, ob hier überhaupt ein Gerät vorhanden ist oder nicht, solange niemand irgendetwas damit macht. Das Gerät scannt aber ständig auf allen Kanälen, wie hoch dort die durchschnittliche Sendeleistung ist. Falls hier eine andere Station sendet oder sowas, wird es diesen Kanal nicht benutzen. Oder zumindest nur, wenn die anderen Kanäle noch schlechter sind. Das Gerät synchronisiert sich mit der Basisstation, also sucht sich den passenden Slot, auf dem die Basisstation broadcastet, hört hier ständig zu. Falls die Basisstation weg ist, ist klar, dann meldet es das. Wenn man dann abhebt, sucht sich das PP die gerade beste Kanal- und Slotbelegung aus, also dort, wo am wenigsten Rauschen drauf ist oder überhaupt keine anderen Pakete vorhanden sind und fängt dort an zu senden. Dort sollte die Basisstation natürlich auch scannen. Zum Sniffen kommen wir später. Wichtig ist auch noch, das Handset initialisiert die Verschlüsselung. Das heißt, wenn das Handset nicht sagt, ich will verschlüsseln, wird auch nicht verschlüsselt. Die Station kann das zwar ablehnen, aber ohne dass das Handset sagt, ich will verschlüsseln, passiert da gar nichts. Probleme beim Sniffen sind zum einen, es gibt viele Stationen, Konsumergeräte und so weiter, die sind natürlich nicht alle synchron. Das heißt, wenn ich auf Carrier 0 die eine Station in Slot 0 am Senden habe, kann das für die andere Station Slot 23 auch auf Carrier 0 sein. Oder die Mitte von Slot 23 oder sonst irgendeinen. In den Paketen gibt es keinerlei Informationen, woher die kommen, wohin die gehen, zumindest nicht in allen. Also das heißt, ich habe nicht wie bei Ethernet eine MAC-Adresse, Destination, Source oder sowas, sondern das Einzige, wie man identifizieren kann, wo das Paket herkommt oder wo es hingeht, ist, es wird auf dem Kanal in dem Slot gesendet. Und zwar sendet, wie gesagt, die Slots liegen 12 auseinander. Also wenn die Station in 0 sendet, erwartet sie in 12 ihre Antwort. Dann, wir wissen, wenn jemand beim PP irgendetwas tut, abheben oder so, und es fängt an zu senden, wissen wir nicht, wo es anfängt. Das heißt, wir müssen alle Kanäle genauso alle Slots und Kanäle genauso abscannen, wie das auch die Station selbst tut. Sonst verlieren wir die ersten Pakete, wo womöglich auch die Authentifizierung von dem Gerät drin ist. Dazu kommt aber Ralf noch später. Zum Descramblen vom B-Feld brauchen wir die Frame Number. Die Frame Number zählt jeden Frame, also alle 24 Slots hoch. Empfangen wir jetzt ein paar Pakete nicht und haben auch keine genaue Timebase, wissen wir die Frame Number nicht, dann können wir mit den empfangenen Daten wenig anfangen. Wir haben zuerst mal mit dem USRP angefangen, einen Sniffer zu bauen für dect. Das ging recht schnell, ein Plugin und ein kleines Python-Skript. Das Gerät, die Kombination aus GNU Radio, USRP mit Plugin und so weiter, kann Pakete capturen, von jedem Channel alle Pakete, also Basisstation und Telefon gleichzeitig, egal wo die liegen, auch wenn es verschiedene Stationen sind, die nicht miteinander synchron sind. Hat allerdings sehr hohe Anforderungen an die CPU. Dann haben wir ein Problem, GNU Radio, zumindest die normale Version, ist nicht Realtime. Das heißt, wir verarbeiten Pakete nicht gleichzeitig, wie wir sie empfangen. Es dauert eine gewisse Zeit und somit können wir nicht genau sagen, das Paket, das wir in Slot 0 empfangen haben, haben wir auch wirklich in Slot 0 verarbeitet, sondern das kann später passiert sein. Das ist auch der Grund, wieso wir keine genaue Frame-Number berechnen können. Wir wissen teilweise nicht genau, ob wir ein Paket verloren haben. Wir wissen nicht wirklich, in welchem Slot wir sind. Und deshalb auch kein Senden, weil wir gar nicht wüssten, wohin und wann. Das Gerät die Kosten für diesen Sniffer liegen bei 1.000 €. Dann haben wir ein bisschen weiter gesucht und haben noch eine schöne Hardware gefunden, und zwar die Common Air Karte. Das ist eigentlich mal ein Gerät gewesen, also eine Karte, die man in einen Laptop steckt, dann hat man eine Basisstation für SIP und kann dann schnurlos halt irgendwo, zum Beispiel auf dem Kongress, wenn wir Eventphone nicht hätten, telefonieren. Der Common Air Sniffer basiert auf einem Linux-Treiber. Der kann nach Stationen scannen, also dann finden wir wirklich nur Pakete von Stationen, sind nicht wirklich synchron, aber wissen, da ist eine Station, die hat diese und diese RFPI. Sie kann aber auch nach aktiven Calls scannen, das heißt, wir scannen nach Paketen vom PP, da das PP nur sendet, wenn es aktiv ist, wissen wir, aktiver Call. Dann empfangen wir aber auch wirklich nur die Pakete vom PP. Wir müssen uns da entscheiden. Dann gibt es aber noch die Möglichkeit, wir können uns synchronisieren auf eine Station und alle Kanäle abschnorcheln und alle Slots abschnorcheln, die dieser Station zuhört und wo sich ein PP melden kann. Das heißt, wenn jemand abhebt, wissen wir, also wenn jemand an dieser Station abhebt, wissen wir, der hat abgehoben, bekommen jedes Paket mit. Das Problem ist, in dieser Zeit bekommen wir keine anderen Stationen mehr mit. Also wir müssen uns dann auf diese Station festlegen. Die CPU-Anforderungen sind allerdings sehr gering, weil das alles hauptsächlich in Hardware gemacht wird. Und da wir genaues Timing haben durch die Hardware, können wir bald auch senden. Die Kosten von diesem Sniffer, von diesem Gerät, laufen auf 23 € raus, gibt es unten beim Föboot-Shop. Angefangen hat das Ganze damit, wir hatten eine Karte, wir hatten einen Windows-Treiber, halt als Base Station für ZIP und keinen Linux-Treiber. Die erste Idee war, schreiben wir dafür mal überhaupt einen Linux-Treiber. Die zweite Idee war dann, schreiben wir doch mal einen Sniffer. Ja, haben wir angefangen zu reversen. Zuerst mal ist eine PCMCIA-Karte, Tuples ausgelesen, einen simplen Treiber geschrieben und Zugriff überhaupt zum Memory bekommen. Das hat allerdings noch nicht viel geholfen. Also mussten wir das Ding erstmal zerlegen. Ein paar Chips waren bekannt, haben wir, wie gesagt, Datenblätter gesucht. Dann haben wir die Karte auch mal komplett leer gemacht, die Platine versucht einzuscannen. Nachher haben wir halt uns einen kleinen Schaltplan gebaut von Hand. Und wir haben auf jeden Fall viel im Windows-Treiber reversed, haben dann die Firmware gefunden, die in den Baseband, den dect-Baseband, der da drauf sitzt, geladen wird. Und haben versucht, den zu aktivieren. Zuerst mussten wir dann mal ein kleines Testprogramm schreiben. Das Dumme war, der dect-Baseband ist ein Prozessor, der nirgends verwendet wird, speziell für dect ist, und das Command-Set ist auch nicht bekannt. Wir haben dann Glück gehabt, die Opcodes, die standen im Open-Source-Treiber drin. Wir konnten dann die Firmware dekompilieren aus dem Windows-Treiber. Wussten allerdings nicht, was die Opcodes bedeuten. Haben ein bisschen damit rumgespielt und hatten dann eine Firmware, die Interrupts geworfen hat. Haben es dann tatsächlich geschafft, die dann auch zu laden, und haben auf Interrupts gewartet. Da kam aber nichts. Da kam lange nichts, versucht. Und nachdem wir etliche Leitungen an das Ding angelötet hatten und die Karte ungefähr so aussah wie da unten, hatten wir auf einmal Interrupts. Danach ging es relativ schnell. Dann hatten wir einen Sniffer innerhalb von einem Monat fertig.
3. Dezember?
Ja,
Weniger als ein Monat.
weniger als einen Monat. Also ein paar Sekunden. Ja, hier noch haben wir noch ein bisschen Hardware-Porn. Also das ist, es gibt zwei Sorten von den Common-Air-Karten. Das ist eine Typ-3-Karte für einen Typ-3 PCMCIA-Slot halt. Die ist etwas größer. Da sieht man das Radio-Modul. Dann ein Standard-PCMCIA-Chip und den Baseband. Also wir nennen das Teil DIP, weil dort also der Dedicated Instruction Processor drin sitzt. Eigentlich hat der die Bezeichnung SC14421. Und die Riesenvorteil von der Common Air Typ 3 Karte, die hat eine LED. Weiter. Das ist das Radiomodul von der Dreierkarte mit hat aufgezeichnet, welcher Chip was ist. Weiter. Da ist die Zweierkarte zerlegt, eigentlich fast derselbe Inhalt. das Radio-Modul ist etwas anders, der DIP ist derselbe, PCMCA ist derselbe und was gerade bei der Common Air 3 Karte auf der Rückseite war, ist hier auf der Vorderseite ist ein kleines EEPROM. Dort steht Seriennummer, also auch RFPI drin. Dort stehen Tunings für das Radio drin. Und dort die benutzt keinen Schlüssel. Eigentlich hat jedes, das habe ich vorhin noch vergessen, eigentlich hat jedes Deckgerät so ein kleines EEPROM. Dort steht, wie gesagt, RFPI drin oder die Seriennummer, die IPI, die IPUI steht drin und teilweise auch der UAK, also der Schlüssel, der verwendet wird. Haben wir uns aber im Moment noch nicht weiter darum gekümmert, weil es geht einfacher. Das ist das Typ 2 Radio-Modul. Jetzt noch ein kleines bisschen zum DIP. Die Architektur wollte ich niemandem vorenthalten, die ist nämlich auch sehr lustig. Also man muss sich das Ganze vorstellen wie ein Stellwerk im Bahnhof. Der schiebt nur Daten hin und her, fasst sie selbst aber gar nicht an. Also man hat Befehle, die sagen nur, die Daten, die da reinkommen, gehen da wieder raus und werden möglicherweise noch durch diese Unit geschleust vorher, zum Beispiel Verschlüsselungen etc. Alle Instructions von diesem Gerät sind 16-Bit lang. Alle Operanten werden auch in diesen 16-Bit untergebracht. Also es ist auf sehr einfachste Weise gemacht. Wenn kein Operand da ist, wird es halt ignoriert, aber trotzdem 16-Bit. Man muss sagen, es ist auf jeden Fall nur ein Co-Prozessor, weil allein kann das Ding nicht funktionieren. In Harvard-Architektur, also wir haben Code-RAM, ganze 512 Byte. Data-RAM haben wir dann 2 Kilobyte, auch nicht besonders viel. Dann interessant, wir haben keinen Akku, wir haben keine arithmetischen oder logischen Funktionen, wir haben keine Vergleichsfunktionen. Um das dann irgendwie doch funktionsfähig zu machen, kann man aber während der Laufzeit von außen das Programm patchen, vielmehr muss man sogar. Und wir nennen das Ding eher dect Interception Prozessor. Und wir haben das Ganze dann auch mal ausgepackt und viel haben wir nicht gesehen, was ist, aber Code-RAM haben wir gesehen, Data-RAM haben wir gesehen und netterweise, als wollten die, dass man es reversed, haben die den DSC direkt an den Rand gelegt, extra, dass man gut findet.
Yeah, now we will switch over to English and I will start with an overview about dect security. So, usually when you got dect devices, you have a base station and you have a phone. And dect is a system which supports row aiming, which means as in GSM, you can take your GSM phone with a German SIM card to the United States and use it in a United States operator's network. And it's automatically row aimed back into your home network. And the same is supported with dect. So usually you got, in all authentication phases, you got two phases. For example, you get the A11 algorithm, which is executed in your home network, and you got the A12 algorithm, which is executed in your guest network. So when you got a device and a base station, both share a common secret symmetric key called UAK. This is marked here in green. And what dect supports is some kind of authentication and key generation. So usually what happens is if a phone should authenticate itself, then your home network chooses a random number called RS. This can be found here. And your home network calculates the A11 algorithm, which gives out a 128-bit immediate key, which is then transferred to your row aiming network. And there the A12 algorithm is computed with an input called randf, which means it's a random chosen by the fixed part, by the base station in the row aiming network. And the result of that is the value called res1, which is an answer to an authentication challenge. So when your phone needs to authenticate, then this A11 and A12 computation is done in your home network, in the guest network, and also on your mobile dect phone. And the random numbers are sent to the dect phone, and the dect phone needs to answer with the correct res1 value. And then your dect phone is authenticated. And also a network can authenticate itself against the phone. In this case, it chooses a value called RS, and your phone, the portable part, chooses a value called randp. And then A21 is computed in your home network, A22 is computed in the guest network. And both algorithms are also computed on the phone. And the phone receives the res2 value from the network and compares it with the value it has generated itself. And if both values matches, then the network is authenticated. So this looks like GSM, with the exception that the network can also authenticate itself. And all this, the complete architecture looks very much like GSM, with the exception that these A algorithms are standardized and they are hardwired into your phone and they are not on a chip card. And what is also supported is encryption using the dect standard cipher. Can be found here. And when a phone authenticates itself, then there's also a key for the dect standard cipher generated, which can then be used to encrypt your phone calls. So in theory, dect security looks nice. Your AK is a 128-bit key, which means it's much longer than usually the keys used on GSM. And authentication of the network and authentication of the phone is both supported. And for every conversation, a new key is generated. And you got some parts in your home network. Your keys don't leave your home network. Oops, sorry. Your keys don't leave your home network. And you got some parts which are executed in the guest network. And in theory, this doesn't look so bad. Now the problem is, because all algorithms are hardwired into the phones, the people who created dect choose to keep their algorithm secret. So these four algorithms, A11, A12, A21, and A22, are called the dect standard authentication algorithm. And they are a secret to the creators of dect and all companies which create dect devices and which build dect microchips and that. And also the dect standard cipher, which is used to encrypt your dect calls. This algorithm is also secret and is not known to the public. And when you create dect devices, you can choose. You can either use these. You can either go to the Etsy and sign a non-disclosure agreement and get these algorithms and hardwire them into your phones. Then you are compatible. You're interoperable with other dect devices. Or if you want to build a closed dect system, you can also replace these 5 algorithms with an algorithm of your choice or algorithms of your choice. Then you got still a dect system, but you cannot be interoperable with other dect devices. Okay. As I said, in theory it's nice, but sometimes there is no authentication and encryption active at all. And there are some cases where only base stations require authentication of the portable part, which means only your phone must authenticate against the network, but the network does not authenticate against the phone. This is usually the case with GSM, and this also happens very often in dect networks. And sometimes you have authentication of both devices, but they do not use encryption. And this means you can run trivial attacks with the right hardware. So what we did, we created a universal dect sniffer. We used this standard PCMCA card to implement such a sniffer. We have written a driver for the Linux operating system. And we have a user space utility which scans for active calls tracks the first call which is found, records all data in the call, and waits until the call is over or until connection is lost, and then it starts scanning again for the next call. And all call data is written down to the disk in pcap files, and we get a special audio player which can then play these pcap files. So when you are next to a dect network and they do not use encryption, and this is the case for a lot of networks in Germany, then you can just fire up these utilities and record every conversation on the network. Currently, the code works. Sound quality is not that good at the moment, but it's okay. And the total costs of this attack tool is €23 just for the card if you have a laptop with a PCMCA slot and you can install Linux on it. So. Step 2. If encryption is used, this tool does not work. In this case, we decided to impersonate a dect base station. So as I said, some phones, and with some I mean all phones I could get my hands on so far, they don't require authentication of the network. So what we did, we created a modified driver which acts like a base station, and well, the first thing you do is you scan for base stations in your neighborhood. You get a listing of all RFPIs of all stations, then you choose a specific station you would like to impersonate, you start a script, and then the driver is configured to impersonate exactly this base station. And what happens is then your driver starts broadcasting the same RFPI, and if a phone is switched on near your laptop, which would like to communicate with the original base station, it will automatically log on to your base station if your signal is stronger or your base station is found first or whatever. And the next thing we need to do, we need to register phones on this base station. We need the IPUI of the phone. This is a kind of identification ID of a phone. We get a second script which registers an arbitrary phone with this base station, and we all run that locally. And after that, the phone is logged in onto your base station, and your base station routes out phones via a SIP provider, so you can register this faked base station with an asterisk server, and this asterisk server can then reroute calls, record calls, whatever, and phones don't require encryption. And so we don't need to know any secret for that. We don't need to break keys. We can just, we can just require authentication of the phone. The phone authenticates, sends us this res value back, and we just accept it, and we don't say anything, and we say that we don't support encryption, and then the phone starts the call without encryption, and we don't need keys for that. So this is a very nice attack tool, and total cost is €23 again for the card. And then you can at least attack every dect system we have seen so far in Germany. We only had a look at perhaps 5 to 10 phones or so, but they all worked with this impersonated base station. So in this case, we can even attack systems where encryption is active but not enforced, and this should be nearly every dect system in Germany. Okay, next step, the dect standard authentication algorithm. The algorithm is used for authentication of the portable part, which means authentication of the phone. It's used for authentication of the fixed part, which means authentication of the network. It's used to generate the keys for the sessions for the phone calls. So every time you start a new phone call and you use encryption, a new key is generated using the DSA algorithm. And it's also used for generating the UAK for the gap devices. So the standard specifies multiple ways how to generate UAK. You can just enter it manually, you can program it into the EEPROM, but if you have dect gap devices, which are, and all modern dect devices are dect gap devices, then the DSA algorithm is also used to generate the initial pairs from a random number and the pin you enter when you pair the phone with your base station. The algorithm is secret, not anymore. We decided to reverse engineer the algorithm. So DSA are 4 algorithms, A11, A12, A21, and A22. And all other algorithms besides A11 are just wrappers around A11, which just cut out a small piece of the output or invert bits of the output or something like this. And A11 is an algorithm which takes a 128-bit key and a 64-bit random number to generate a 128-bit random output. And A11 uses 4 different block ciphers we decided to call Casable because we had a name for these block ciphers to generate the output. This is the structure of A11. So we got these 4 block ciphers. The key always goes in on the left side, and the input goes on from the upper side, and the output comes down on the bottom side. And key is the 128-bit key used as an input for the A11 algorithm, and rand is a random number, which is depending on where the algorithm is used in the dect protocol, called randf, randp, or rs. And this is the logical structure how the output is generated. Yeah, ref just reverses the byte order of an input. These signs here just means you concatenate your input, and with these brackets, I mean cut out bits 96 to 127 inclusively from the value key. And yeah, this is the A11 algorithm, and we also have a detailed analysis of the Casable block cipher. It's a substitution permutation network. Input is 64-bit, the key is 64 bits, the output is 64-bit, and the internal state also has 64-bit. As a key scheduling function in the block cipher, a bit permutation is used, and each variant of these 4 Casable block ciphers only differs in the bit permutation. And the round key is just added with an XOR to the cipher. And a single invocation of the cipher does 6 rounds in total, and each round consists of the addition of the round key, an application of an S box, which we also know, to the internal state, and then a kind of butterfly mixing. So there are 3 different mixing functions which look like a butterfly network, and which mix each bytes in the states with another byte in the state. And at the end, there is no final key addition, which reduces the strength of the cipher to only 5 relevant rounds. We did a little cryptanalysis on the cipher. When you first look at the block cipher, at this Casable cipher, you think that there's full diffusion after 3 rounds, so after half of the rounds. But if you look a little bit more closely, you see that it takes at least 4 rounds after you get full diffusion. Full diffusion means that every bit in the internal state depends on every bit on the input and every bit of the key. And we were able to do some linear cryptanalysis attacks for 2 to 3 rounds version of the cipher. We were able to find an algebraic attack which can break 3 rounds of Casable. And we also have a differential attack on the full cipher, which sees about 16 pairs of inputs and outputs, where you need to choose the inputs. And you can then break the cipher with an effort which is comparable to 237 invocations of the block cipher. So in theory, you should need 265 invocations of Casable to break Casable. But with this attack, you can do it with 237 invocations. This work has been mostly done by Stefan Lux on the differential attack. And however, this has no direct impact on the dect standard authentication algorithm so far. We know that we can break the block cipher used in DSA, but we need 16 pairs with chosen input to the cipher, and we couldn't extend this attack yet to the full version, to the version used in the DSA algorithm, because in DSA you have this casable block cipher somehow chained. You have at least 2 invocations of the casable block cipher until you see a piece of output. As a summary, we have written a paper about this, a text on the dect authentication mechanism, and this paper will be presented at CTRSA next year in San Francisco. The paper contains a description and analysis of DSA. It contains pseudocode of DSA, so you get everything you need to implement DSA yourself. We have C and Java implementations of the cipher, which will be soon available at detector.org. And we also have a high-performance VHDL implementation for FPGA cards of the cipher. This is not yet available, but it's already running, and I think we are somehow close between 226 to 230 invocations of the cipher per second, depending on the FPGA. This will most probably be available soon. So now I will give over to Ralph.
Okay, so for the dect standard cipher, we weren't able to find any software implementations. So for DSAA, there are software implementations, and that's how it was reverse engineered now. What's funny is that the ETSI non-disclosure agreement specifically says that you should not try to register any intellectual property, such as patents, on this cipher, which happened in 1993 when Alcatel filed a patent in Spain, which then became a patent later in 1999 in the US as well. And this leaked significant amounts of data on this cipher. Hang on, sorry. So what we learned from this patent was that we're dealing with an irregularly clocked combiner with 1 bit of memory. We have 3 irregularly clocked LFSRs that are clocked either with 2 or 3 clocks, and they are of length 17, 19, or 21, and 1 regularly clocked LFSR of length 23. Actually, the mapping of the lengths was not known at that time, sorry. So we know the length from the patent of all of the registered, but we didn't know which one was regularly clocked. It was just a guess that the last one would be regularly clocked. So they furthermore described how to do the key setup, and they also had this very strange thing where they check whether a register is 0 after 11 steps of this pre-ciphering step, they call it, which is basically blank rounds of the stream cipher where you don't generate output, but you irregularly clock it. And when that happens, they loaded 1 into every register. Why they do it that way, we don't know. Maybe somebody misunderstood how stream ciphers work, specifically LFSRs, because you can check that like in the very first clock already. So then we had people looking at parts of the chip. So the first tricky part was find out which chips actually do implement this dect standard cipher, because first we found, well, okay, this phone does not encrypt with the space station, doesn't encrypt with the other base station, and well, finally we found something, a combination where we knew that we actually had DSC. So the chips were decapped, they were sent over to FlyLogic, as I understood. There were some strange transport problems which like slowed down the whole process for a long time, and I think they were thought to be lost at a certain point, but then reappeared. So this was done by Starbuck, Carsten Null, FlyLogic, and Mazu, which is Matthias Wenzel. And these guys managed to recover the tap positions of the LFSRs that way. But then there was a problem with the clocking function because the logic didn't make sense at a certain step in this diagram. So simultaneously, we began getting greater knowledge of this Cytel CPUs, and we found a product that uses DSC as well, and we looked at that firmware, disassembled it, and looked at other firmwares which didn't support the DSC, and basically looked, oh, okay, well, there's these strange instructions that start with D underscore something, and there's something called D underscore LDK, well, might be load key, and we did a little bit of fumbling around with that, and then there were instructions called LDS and WRS. We didn't know what that was at first, but then we tried executing these instructions on certain parts of the memory that we could read out from the PCMCI part, and we found that we had patterns that changed in a strange way depending on the number of cycles that we waited. So we were like, okay, this could be actually the internal state of the stream cipher, because you may want to save the internal state so that you can directly start streaming out the frame at the exact same moment, synchronized with the DSC. And because, I mean, key setup takes time, you want to do that beforehand, write out the state, and get it back when you need to write out the frame. So what this allowed us to do was we were able to single step through the key loading of the stream cipher to determine the feedback taps. This was already done by the other hardware people, but just to verify that these were correct, and also because I wasn't able to read the output properly. I tried drawing diagrams from that, but I failed. So then the next thing was we figured out that we could actually load a state that was not generated by the load key function. We could just load arbitrary memory. And this allowed us to isolate which bits were actually involved in generating the clocking sequence. So by using basically like 1-bit differentials, we found out that this was only a limited number of bits, and we were able to interpolate the clocking functions using a computer algebra system, which is kind of, well, embarrassing because the function was linear, so we could have seen that with bare eyes, but we were just tired at the time. At the moment, we're still missing the output combiner, but that's for the reason because we haven't written firmware for sending yet. This is something that we know that we can do, we can pull it off, but we just haven't had the time yet. So what we need to do is we need to have one side that sends out a frame in, with encryption and without encryption, and then we will sniff it with another laptop, and then we'll be able to get known plaintext, and this way we'll be able to get to the combiner function as well. Now, here's a diagram of the DSC. People of you who have looked at the A5 algorithms may find that it looks a little bit familiar, except for the tap positions, and one length of the output registers. And it actually was designed in at around the same time that A5 was designed, so we figure it was designed by the same group of people. What you see in orange are the tap positions for the Galloway-style LFSRs. What you see in green are the positions that are used for the clocking. So what is done is that each of the registers gets tapped at the middle bit, just like the A5 functions do that. A5 1 and 2, not 3. And then you tap 3 bits of the of the fourth regularly clocked register, and you get the clock, you get the information how to clock one of the irregularly clocked registers by looking at bits of the other irregularly clocked registers and one bit of the regularly clocked one. So this is kind of annoying because we had hoped that they would just use R4 for the clock control, because then it would have just been a copy and paste attack from A52, and this thing would have been trivial to break. Well, this unfortunately is not the case, or fortunately, whichever way you look at it. And moreover, it has a much larger state than A51, as A51 just has 64 bits of internal state. This cipher has 80 bits of internal state. And this means that we cannot directly transfer these attacks as well. But the short pre-ciphering phase gives us hope. In A51, you have 111 steps before you generate the first output bits that are irregularly clocked. Here, you only have 40. Some of you may say, okay, well, but you step 2 clocks at a time. This doesn't matter. This just, I mean, it's a linear thing, so you can just transform it into another linear function that, into 2 linear functions, one that steps 2 and one that steps 3 times. So this is, the number that is important is the number of clocking decisions, and this is 40 for this cipher. So at the moment we don't have an attack yet on this, but I'm pretty confident that there are people, maybe here in the audience, maybe somewhere else, who will find an attack on this cipher in the next year. I'll be willing to bet money on that. Now, I'll come to something different, which is actually a practical way to attack dect and, well, get your hand in the cookie jar very deep. There's something called UAK allocation in the dect standard documents, and this is basically the pairing mode, where you first bring together the handset and the base station for the first time or for the second time or whatever. And in this process, you generate a master secret between the base station and the portable part. But the problem is, this depends only on an authentication code, which is usually restricted to 4 decimal digits that is shared between the FP and the PP, and 64 bits of a random value that is generated by the base station. Now, the problem is, where does this entropy come from? So, here's a diagram again. So, this is used, I mean, you have this procedure because of gaps. So this is a generic access profile, which makes all of the more recent dect phones interoperable with each other. So what you have is you have one step where the fixed part sends a message to the portable part and says, hey, I want to allocate a key. Here's a random number from me, and here's another random number, RS, from me. And in the next step, the portable part answers with, okay, here you have a random number from me, and the result for the random number that you gave me, because I know the same secret key, it's the same authentication code that you do. And in the last step, you have an authentication reply, which depends on the value RS, which is the same value as in the first step, and another value res2, which is computed from the random value that was sent by the portable part, and together with the authentication key. Now, let's look what these guys use for generating random numbers. This is a widely used dect stack, and this is an example. The problem is it doesn't get much better than this, or worse. I mean, it depends on your perspective. So let's count. There's a 16-bit integer up there, and then there's another 8-bit integer. So this is all the entropy that they use. So this is 24 bits of entropy. You think, actually it's 22, because some of those values collide. So what this means is we can grab off two challenge response pairs, actually triples because you have RS and RANF, but we call it pairs, and responses, the rest one, of the air. Then each pair will act as a 32-bit filter for us. We can iterate over all of the 4-digit pins, and in a very low number of DSAA operations, we will be able to get the master secret. If we assume that, as many people do, they just punched in 4 times 0, or it was prepared that way, then it's actually down to 2 to the 24 DSA operations, which this machine here, an Intel Core Duo, can do in less than 50 seconds. And this implementation of DSAA is not optimized at all at the moment. So what this means is you have full access. You can impersonate handsets, base stations, decrypt encrypted calls as long as nobody is repairing the whole full Monty. This is game over. So I just gave you one example. On the slides we have more. At the moment we have just 3 because it takes time to reverse engineer firmwares and find the random number generators there, but they are classes, so there's only a small number of these dect stacks actually around. And what you can do is you can classify or you can detect what stack is being used just by looking at the RANs that gets emitted by the base station. And this basically you can just grab like a challenge off the air, then you do a grep over a text file, and well, okay, this is manufacturer XYZ, or actually, well, stack manufacturer XYZ, and I'll be able to break that in 2 to the 30. And this is another one, and I'll be able to break this in 2 to the 36. There's another option that you have. If you have access to the equipment manufacturer codes database, that's something that's done by the ETSI, where they give out numbers of the RFPI, 16-bit numbers, then you can directly go from an RFPI to a manufacturer and therefore to the dect stack as well. But the problem is there's only 2 to the 12 devices per EMC, so there's more than one EMC per manufacturer. The database, unfortunately, is not available. There's also the problem that you have prepared phones. So basically, when you just buy it in a store, it will have been prepared in a factory and probably not using the same procedure. This is uncharted territory for us thus far. We know that we can read the serial EPROMs of these prepared phones. Most of them actually have test points, which we figure were used for personalization in the battery case. So you can just, if you get the right pins, you can just use I2C to read out the EEPROM. And, well, we expect externally generated non-randomness here as well. But we haven't looked. I mean, this is something that you guys can do as well. We want you to join us. And now we come to the last thing that has happened only in the last couple of weeks. We have gotten the author of Kismet interested in dect as well. And the next generation Kismet, which is, I think, to be released very soon, most probably will support dect as well. So thanks for that, Dragon. Thanks for that, Connor. Okay, now
okay, we need to speed up it a little bit. So other stuff which will be soon on detected.org. The website should be up within an hour. Paper about DSA cryptanalysis. We will hopefully get soon our FPGA implementation out. We have the Kismet plugin. We will hopefully reverse engineer the DSC soon. We will try to put up the GNU Radio plugin soon. We have some infos about the AVM Fritzbox 7270, which is also nice for playing with dect because it's a Linux device with a dect stack. And we would like to put up more infos about specific phones soon. If you're interested in the Common Air card, you can buy them at the Filbert shop here locally downstairs. I think price is 23 euros or so. Or if you are watching this via video, then you can buy them on eBay. There are enough cards available. We would like to thank Chaos Computer Club for great support of the project. Of course, also our universities. And Mazu for the great help with the Linux driver. Starbuck, Carsten, and Flylogix Engineering for the chip reverse engineering part, and very, very especially Alcatel for pulling this very nice dect ciphering device patent, which has really supported us a lot. Definitely, a lot of this work wouldn't have been possible without this patent, and we would like to thank many other people. You can contact us at team@dedected.org.
Actually, we just wanted to give a short demo. I don't know if the time is sufficient still. Okay, it's not sufficient. So you can come up on stage. I wanted you all to pick up the phone while we have the sniffer and live running, but okay, you can come up here a few minutes.
Okay. And in the case you are from the United States, you can contact Jacob Applebaum to get one of these cards in the United States.
Yes, so that's another thing. So the driver not only supports dect phones that are sold in Europe, we've also made sure that it supports dect 6.0 phones as well.
Okay.